Sonic, the heart of your system.
Hi and welcome back to a new video, finally part 3 of the Tescan video series. Today we will be able to take a closer look at 14 and 17 nanometer transistors. And before we start and get into this, nowadays you have the choice of Intel CPUs, you can get them in 14 nanometer, and you can get AMD CPUs, TSMC CPUs with 7 nanometer. Those are the two choices you have. But what do those numbers mean? And what do those numbers mean to you? Ideally, at this point of the video, maybe just leave a very tiny comment down below and let me know what you initially think or thought about those numbers. Before we check out the Tescan footage step by step, how we took apart the CPU and took the shots of the 14 and 7 nanometer transistor, a quick look at how does a transistor nowadays look like, because this will be important so you can also understand the images we're getting from the Tescan microscopes. Until the year 2011, most of the transistors were 2D transistors or planar transistors, and they are very, very simple. The most important components are source, drain, and gate. To simplify it, if you run a voltage through the gate, you can have electrons flowing from source to drain. And with this function, the field effect transistor, also called FET, can work as a switch and so allow to have the states 0 and 1. In the semiconductor industry, you're trying to scale down things further and further. You try to make it smaller and smaller to pack more transistors on the same area to increase the performance. The only problem is if you decrease the size of the gate, if you make it even smaller, you have something which is called sub-threshold leakage. And this describes a phenomenon where electrons can flow from source to drain even though there is no voltage directly attached to the gate, and this is causing a lot of leakage with the CPUs. The FinFET is a field effect transistor which is using fins, and it's a 3D structure. The fin has the function of source and drain, and in the middle of the fin we have the gate right above the fin. This way the gate has direct contact over 3 sides, from the left, from the right and from the top, over the source and drain channel. The function is the same as before. If you now run a voltage through the gate, the channel underneath becomes conductive and electrons can run from source to drain. In reality, we don't only have one fin or one gate, we have multiple fins and gates. The reason for that is that it depends on the exact purpose of the transistor, on the switching speed, and on how reliable it has to be. Then you improve it with multiple fins and gates. In the previous part, we were preparing the CPUs to have them sitting inside the scanning electron microscope to be ready for everything that we're doing right now. And now step by step, I will explain what exactly we did. CPU is now sitting inside the scanning electron microscope, and the goal is that we cut a very thin fin out of the chip to have electrons running through this very tiny part so we can see through it and see the transistors. I'm just going to show the process with the 7 nanometer TSMC or AMD CPU. We of course did the same process with a 14 nanometer 10900K CPU, but the process is exactly the same. That's why I'm just going to show the AMD part right here. To be able to cut the very tiny and thin fin out of the lamella, we first have to prepare the chip. On the left side you can see how an arm is moving inside the chamber, and that is the GIS, or also called gas injection system. You can now see 5 tiny pipes on the right side which are directed towards the chip. Out of one of those pipes we will have a platinum gas reaching the chip, and that will be able to have a tiny layer building up. We have to perform this step to protect the chip from the top. This will allow easier cutting through the chip later and also give it a tiny bit more stability. The gas is now reaching the surface, and at the point where it's hitting the focused ion beam, we will have the structure building up. On the left side you can see a rectangle which allows easy positioning of the focused ion beam, and therefore how and at which position we are building up the structure. And on the right side you can see the live SEM image where you can see the platinum layer building up. Everything of course is time-lapse for you because this process in reality is taking several hours. In the next step we are defining where exactly we want to cut out the lamella out of the surface. In the left side you can see again blue rectangles where we define exactly where the ion beam is hitting the surface and where it doesn't hit the surface. Again, this process will take several hours. Now after our successful mining, you can see on the images that we have cuts from the top and from the bottom and a small cut from the right. The cuts are performed with an angle, so we are cutting also underneath, and the lamella is just hanging on this very tiny piece on the left. At this point, the lamella has a size of only 100 micrometers length. That means the thing that you're seeing on the picture, which looks kind of tall, has only the length of 0.1 millimeter. If you would put this on your finger, it would just look like a tiny piece of dirt. As comparison, now we are seeing an image of the lamella of the 10900K. After the lamella is just hanging in the room, we have to make it even thinner because we want to use something that is called stem. And in this process, we will have electrons running through this lamella. It's kind of like a light microscope where you would have light running through what you want to look at. And in this case, we're just running electrons through our lamella. And you can probably imagine that this thing has to be extremely thin that the electrons can make their way through the material. To be able to see it inside the stem, we now have to somehow get this lamella out of the hole and attach it to a small holder. For this process, we're using this very tiny needle and attach the needle with platinum again at the lamella. At this point, also always keep in mind how tiny everything is right here. Again, lamella has only a length of about 0.1 millimeter, and just being able to place this needle so closely and precise to this lamella is already mind-blowing. Once the needle is at the right position, we again have gas running across this area, and once it's hitting the ion beam, we will have platinum on top. This way the lamella is connected with the needle and we can now cut off the lamella at the back part. In the video it kind of looks like everything is melting, which is kind of funny. Like it looks the silicon is melting, but this is just because, again, this is a very fast time lapse and it would take a very long time again to see this in real time. Now we're moving the lamella on the needle to the holder, and we're trying to attach the lamella again with platinum to the holder. And at this point it's just very important that you're extremely careful placing the lamella and the needle not too close to the holder, because if it just touches this very slightly, it immediately breaks off and all the work has to be repeated. That happened to us in between, and it's just one full day of work gone and you have to perform everything again from the start. Once the lamella is close enough to the holder, we are again using platinum to attach the lamella to the holder with the ion beam, and then we are also using the ion beam to cut off the lamella from the needle. And finally we have the lamella hanging at the holder in the correct position and we can proceed working on it. As mentioned previously, we have to try to make this lamella as thin as possible. In reality, we will need about 200 to 300 nanometer thickness to be able to see the structure within. It's not important to keep the whole lamella very thin, it's just necessary to have it on a very tiny part. And you can now see in this image how rugged the surface of this lamella is it's quite impressive already, just seeing those images from my perspective. And if you're paying very much attention, you can see a gray, very thin layer within the lamella, and that is actually where our transistors are located. Finally, we can use the stem, and as I said before, that is used to run electrons through the lamella, and we are able now to see AMD or TSMC 7nm FinFET transistors. On the first look, it's probably quite difficult to figure out what exactly we're looking at and which part is a transistor. Our goal was to cut through the level 1 cache of the CPU, because the level 1 cache, for comparison, makes it a little bit better to compare the CPUs. If you cut somewhere through the logic, you'd certainly have differences between Intel and AMD CPUs, and comparing CPUs directly probably makes it easier just to cut through the cache, which is fairly the same on the CPUs. And we were trying to perform the cut through the gate, so we're able to measure the gate length. As a quick reminder, in between, that was the FinFET transistor, and we're cutting through the FinFET from the side. What you can see marked green in the image will also be marked green now on our cutting image, and the dark areas which we can see within, those are the gates. That means we're seeing a lot of 7nm transistors sitting next to each other where we cut through. And now we're just measuring some metal contacts, should be copper in the CPU. For the future, if it's an Intel 10nm, should be cobalt. That was a size of 18nm, which is just sitting right above the transistor. And if you're measuring the gate height, we have a height of about 87nm. Now going back to the previous image, we see all those transistors sitting next to each other. On the bottom right, you see a scale with 200nm. Just keep your eye on the scale, because we're switching to a different view now, but the scale will be exactly the same of the 200nm. And you can see not much changed if you kept your eye on the top left corner. The dark area again are all the gates where we cut through. But the thing is, when we just switched to the different view, we switched from the 7nm TSMC to the 14nm +++ 10900K. And some of you might think, hey, but that's not half the size or double the size, depending on your perspective. And that is exactly the point. But let's just compare it a little bit more in detail, like next to each other and above each other. If we measure the gate length of the 10900K, we have a gate length of roughly 24nm. And if we switch back to the AMD or TSMC CPU, we have about 21.4nm of gate length. Here again, comparison, Intel 14nm +++ on the left, AMD or TSMC 7nm on the right. Gate height looks to be kind of similar, but if we're moving the pictures above each other, we can clearly see that TSMC 7nm is tighter and smaller than the Intel CPU. You might now say or think, hey, who of them is lying to us? Like, why is an AMD 7nm CPU not half the size of a 14nm Intel CPU? And all I can say is it's not that simple. We have a FinFET transistor, which is a 3D structure, and obviously a 3D structure has more than just one dimension and one parameter. And the thing is, judging a transistor or a structure by one number is stupid. It's as stupid as what we just did. We just measured one gate length, and compared it for a 3D structure, and that just doesn't make sense. Let's go back to the question from the beginning. What does 14 or 7nm mean? Back in the days, it was describing the length of the gate. You can see it in this table. We had a gate length of 500nm, and the process was also called 500nm. There is an additional size, it's called half pitch, and that's the distance between source and drain. At the 500nm production, this was both the same, and that's why this process was called 500nm. But if we look through the years down to the 14nm in 2018, we see that the 14nm has no relation anymore to gate or half pitch length. Now, which size does 14 or 7nm reflect in your CPU? The answer is simple, none. You just have to understand that this naming scheme just reflects a process. It's just a process which is called 14 nanometer or 7 nanometer. It just could be called the Intel Blueberry 5 construction, and it could also be called the AMD Strawberry 3 process. It would give you the same amount of information as having 14 or 7 nanometer. However, this figure reflects process history. Just looking at, for example, 90 nanometer, 65, 45, 32 nanometers, all of those have the factor 0.7 within the name, just going from like 90 to 65. The reason for that is we're looking at a structure on a surface. And if you have a factor of 0.7 in length on the surface, like 0.7 times 0.7 equals about 0.5, which means that we have double the amount of transistors. And that's the point where they decide to give the process a new name. It's just the point when they have the better tolerances or where they figured out a new process to make the transistors sit closer together, but not necessarily even closer together. It could just be a different process itself. For example, Samsung at a certain point when they were having 20 nanometer, they moved to 40 nanometer process just by switching to FinFET transistors. It was just switching to a different type of transistor. The metric was not necessarily changed, but just switching to a different transistor. That's kind of interesting. I mean, most of you, or I hope at least some of you, were wondering, like, why is a 3700X with 8 cores not twice as fast as a 10700K, for example, which is also 8 core, but it's 14 versus 7. And that is because you just can't, with a single number, compare processes of different factories. That is not how it works. You can compare, for example, 14 nanometer Intel with 10 nanometer Intel. That's something you can do. You can compare 12 nanometer TSMC with 7 nanometer TSMC. That's something that works, but within the different factories, you cannot compare this. So let's assume that Intel figured out how to pack their transistors denser together, and by the factor 0.7 they decide to go from 14 to 10 nanometer. But the thing is, we don't know where they started from. We have no relation to this factor. And for example, if you compare the transistor density of Intel 10 nanometer, which is about 100 million transistors per square millimeter, with TSMC 7 nanometer, which is about 91 million transistors per square millimeter, you would assume that Intel 10 nanometer is faster, but that's not essentially true, because it depends how your transistors are looking, because at different parts of the CPU you have different transistors with different sizes and different shapes. It depends if it's a NAND cell, if it's an SRAM cell. Let's assume you have a CPU with 200 megabyte of cache. You have an enormous cache part of your CPU, and in the cache you can pack those transistors so damn close together that would boost up your transistor count on the CPU, but would it make your logic faster on the CPU? We have no idea. And now to go back again at the end to the question from the start, what does 7 or 14 nanometer mean? I have no idea. It's just a process, it's called this way, and there is no standard in this industry, which is kind of sad. There should be a standard which kind of defines a metric on the CPU, like transistor density, whatever, some kind of standard, but as long as there is no standard, this number doesn't reflect anything, shouldn't matter whatsoever to a consumer. If you're buying a new CPU, just look at the benchmarks. If there is a review for the start, you see exactly, I don't know, Cinebench 15,000 points on AMD Threadripper, and that's great, that's what I want to have, then just go and buy it and just don't care about other numbers, because it's not going to tell you anything. At this point, I also want to thank Tescan for the possibility to cut through the CPUs and to analyze 7 and 14 nanometer CPUs. Was absolutely impressive, very interesting. Thank you very much for the possibility to be in your office and have the opportunity to cut through those CPUs and to look at it, and of course also to share the information with you. I also want to point out that this video was delayed by the fact that I sent all the results to AMD and also Intel and asked them about a statement, like what does 14 or 7 nanometer mean to you in this regard. There was no clear answer. I had a very nice chat with an AMD engineer. Thank you very much for your time, that you also looked through the pictures, because I was not sure at a certain point if we're looking at the right things, and he just confirmed that yeah, those are the correct transistors and everything. That was cool. But he also pointed out, actually he pointed out what we were discussing in the video, that you cannot judge like 7 nanometer by a single digit, like we measured the gate length. And yeah, but thank you for your time, AMD engineer. It was absolutely great to have the chat, and there was not really any reaction from Intel, which is okay, I guess. But anyway, yeah, thanks for your time and looking at this video. I hope you enjoyed it. See you next time. Bye.